Hi everyone, let's solve this problem. Word search. Given an m cross n grid of characters board and a string word, return true if word exists in the grid. The word can be constructed from letters of sequentially adjacent cells, where adjacent cells are horizontally or vertically neighboring. The same letter cell may not be used more than once. So now let's try to understand this question. So let's say we are in this case searching for A, B, C, C, E, D, and this is a M cross N grid. M cross N grid. Let's consider I take a particular cell. Let's consider F as a cell, and let me consider this as a particular row and column. So anything above it will be r minus 1 comma c, same column and previous row, and below it would be r plus 1 comma c, and ahead of it would be r comma c plus 1. We are moving our columns, and this side it would be r comma c minus 1. We are reducing our columns, right? So this is how our direction will be. So at any given cell we can go in all these four directions. That's what they mean by saying that where the adjacent cells are horizontally or vertically neighboring. So that's all they are trying to say here. Now I hope the discussion about rows and cells is clear here. Now let's try to understand how we can check it. Let's say for example I start, because my word is here, I started 0, 0. Now let's say I go to S. So it's A is matching, so I will increase my index. It will be B and S. So this is not going to match, and obviously we cannot go towards this because this is an error bound, and this is also an error bound. So I'll be moving only in the direction of B. So in this direction I see that B is also matching, right? A matched, B also matched, and now I have two options: either move F towards F or C. Let's say I move towards F. F and C are not matching, so I will again move to C. C is matching. Now at C I still have the options of C and E, right? And also let's also understand I can also go back, right? But this is not allowed. This is what is already mentioned. The same letter cell may not be used more than once, so we cannot go backward. So in order to know if we have already visited that cell or not, what will we do? We will create a set which actually traces our path from where we are coming. So if the path already has a particular cell, we will not revisit it. So that's the entire logic here. So again, it's a backtracking solution. So we will start at every cell and we will explore all the possible things. Let's say for example I'm starting at A. I can go towards S or B. B worked. Now I will not go any further here, but here I have C and F. I have explored C, it is not the right way, so I will go towards C. Again at C I have C and E as possibilities. E is not going to work out. So basically I will keep trying to explore all the paths, and once I find the entire string, then I would stop. So how do I know if I found the entire string or not? If my word dot length is equal to, if my word dot length is equal to the index, right? We are also traversing over this word, so we will be traversing using a particular index. So this index will determine if we have reached the end of the letter or not. So once we find the entire word, we can just return true from there. So now let's try to code it up, and if you want to understand more about backtracking, how we explore all the paths, you can go through the video of subsets. It will give you more idea. So now we will first have to get rows. Rows is nothing but board dot length. Let calls is equals to board of 0 dot length. So why can we take directly board of 0 without checking null checks is because we have that m and n will be at least 1, so we don't have to worry about it. So now once we get this, we also have to have a path which is a set, right? And we are going to call a backtracking. And how are we going to call it? We are going to iterate over all the cells. For a two-dimensional grid, how are we going to get a cell is board of I comma j or r comma c. So r is less than rows, r plus plus, and for let c is equals to 0, c less than calls, and c plus plus. So with this we will call backtrack function. We will have to have a board word, we need path, we need rows, we need columns, and then we will have to pass the current row, current column, and then also index of a word will be initially 0 because we have to explore all the letters of a word given to us. So we will start our index at 0. So if it returns 0, if this method is true, then we will return true from here, else at the end we will just return false. Now let's try to write the backtrack method. So we need board, word, path, rows, columns, row, column, and index. So our base case would be if index is equals to word dot length, that means we have explored the entire word, that means we can return true from here. We also discussed about the error bounds. If r is less than 0, okay, row is less than 0, or column is less than 0, or row is greater than or equal to rows, or column is greater than or equal to columns. In these cases also we have to return false because they are kind of, so let's say for example in this case these two are not allowed, right, going to previous elements, and let's say for example here we are not allowed to go towards these two because they have already reached the bounds of the given grid. So these are our bounds. And the other case is, let's say word of index is not equal to board of row comma column. In that case also we will return false. And the other one is if path already has our key will be nothing but row and some delimiter, and then we have a column, right? If either of this case is true, then we'll return false from here. And then we have to insert our path because we are going to explore. If none of these are matching, that means we are going to explore that particular cell. So we are going to mark it as visited using our function where we have this, not a function, a string where we have like row hyphen column. We have inserted it. Now we will get the result. Result is nothing but we have to board, word, path, rows and columns will be same. So row plus 1, column, index plus 1, or again it's the same thing with row minus 1, and same thing with column plus 1, but row will be same, and then we will have this column minus 1. So we are exploring row plus 1, row minus 1, column plus 1, column minus 1. We are going to increment the index because whenever we are at a particular cell, we have already explored one particular letter which is a valid matching. That's when we go to the next. So that is the reason we are incrementing index all the time. So if one of them is also true, that's the reason we are using OR. What will we do? We will do path.remove of, or yeah, path.remove, or we can just take new set here and then we have set and we will have delete. And now in this case we will return result after finishing the entire thing. Now let's try to run it up and see. Okay, it should be add, sorry, my bad, because it's a set. If it's a map, we have to use the set. Now let's try to submit it. We are able to submit this code. Now let's try to understand the time and space complexity of this solution. Time complexity of this solution is nothing but we are iterating over all the rows and columns, which is nothing but m into n. Into, and let's consider L as the length of the word. So we are in the worst case, when the word is not present in the grid, we are going to explore all 4 paths, and every path is going to take L time, because L is the length of the L into L into L. So this is nothing but 4 power L, right? The space complexity of this is nothing but L, because the recursion depth will be L at max, because L is the length of the word. And even if you consider the path set space, it would be at max L. L plus L, it would be L again. So this will be the time and space complexity of the solution. I hope the solution is clear and you understood it. Thank you.